Okay. In last class, we have solved one problem, right? Now today we'll solve problem 2. Then we also derive one formula, and let's see how we can do it. 1 second, let me close one door. Okay, you see problem 2, there is a cross section of a column right over here, kind of T section. And it's saying length of column is 4 meter. 4 meter, and Young modulus, that means value of E is 200 gigapascal, and compressive yield strength is 60 gigapascal. Now it's saying calculate allowable buckling load. That means you need to figure out the value of P critical, right? P critical. So if you got sigma critical, you can figure out the P critical by multiply by cross-sectional area. And it's saying if both end is hinge, that means both end is pin. So you know in that case value of C will be 1. And length is given. So L will be 4 meter, right? And this 200 will be Young modulus. That means this is value of E, and 60 gigapascal is the compressive yield strength. That means that one is given sigma Y. Some book write down also SY, but same thing. Some book write FY. So SY, FY, the same thing. Number B, it's saying solve part A. If one end of the strut is fixed and other end is free, and length is 1 meter. Okay. So what we need to do? We need to figure out this value L by low critical. If length is L by your L by K is come less than this value, then it will be short column. If L by K is greater than L by K critical, then it will be a long column. Okay, that we need to figure out. So to figure out L by K, we need to figure out area. We need to figure out cross section, and end condition already given. Okay, so let's see. I can share the MathCAD file with you. See right over here. Okay, so length of the column L equal to 4 meter. For pin to pin support C equal to 1. And compressive yield strength, I put SY, you can put sigma Y, same thing. Sigma Y, FY or SY, same thing. So this is compressive yield strength. Modulus of elasticity, you convert in gigapascal to pascal. This data is given. Now how do you need to figure out? P critical, if both ends are hinged, that means pin support. And P critical if length of the column is 1 meter, and also one end free and other end fixed. Then you need to figure out this value. Now, how we can do it? At first, we need to figure out the area. We need to figure out the I minimum, because K equal to square root of not this one, square root of I minimum divided by area. So how will we get I minimum? You need to figure out the inertia, both x-axis and y-axis, and you need to figure out the area. So area you can easily figure out. You just make 2 sections, then figure out the area, and I got this is the area. Now, this cross section is not symmetric, right? Symmetric about vertical axis. That means if I make a vertical axis at the mid section, so left side and the right side, your area is same. But you see, if I make a horizontal line, then at the top and bottom area is not the same. Okay. So what need to do, and we don't know where is the CG, location of the CG. Since at the top area is little bit more, we are getting the area CG is right over here. It might be below this point and a little bit upper point. But how we can figure out the area and location of YCG? This is the formula, and you already know from your engineering mechanics, your knowledge applying over here, that YCG equal to sum of AI, area 1, area 2, into YCG of that area divided by sum of area. So you see YCG, we divide two area. This is one area and the bottom one other area. So at first you take the area 1. Or area 150 millimeter into 20 millimeter. So this is area 1. Into its CG. You need to figure out. So what is its CG from the bottom? Its CG will be of this stripe will be at the midpoint, right? So CG from the bottom will be around right here, yeah, at the midpoint, right? So you see 100 and this thickness is 20, so 110 will be YCG. That's why we multiply by 110. 150 into 20 into 110. Now, then take the bottom one. Bottom one, what will the area? 20 into 100. 20 into 100. And what is the YCG? Midpoint of YCG will be midpoint over this point, right? So I multiply by this 50. 100 into 20 into 50, this is 150 into 20 into 110. Divided by area. So summation of 150 into 20 plus 20 into 100. So you get YCG 86 millimeter. That means the YCG from the bottom is 86 millimeter. You see in the right side figure, right over here, I mentioned YCG equal to 86 millimeter. And XCG should be at the middle. That means at the middle of the flange. Okay. Now we need to figure out the IXX and IYY. Since we should not teach you how to figure out the IXX and IYY, because this one already you know in your engineering mechanics class, but still we are showing you over here how we can figure out the YCG. Okay, I'm sorry, I figure out IXX and IYY. So at first I like to figure out IXX. So what do you need to figure out IXX? I need to figure out IXX respect to CG. This is the CG. That means respect to this line IXX. So what we'll do? We'll figure out we'll take two area, top and bottom. So at first take the top one. 1 by 12 B H cube. So you see 1 by 12. What is my B? 150 millimeter. 1 by millimeter. H is 20. So 1 by 12 B H cube. Then plus AD square. So area obviously you know 150 into 20. And what is the D square? D square will be, we are working with the top area. So this will be distance between the top area and this seat. And this seat. Okay. So this distance will be how? The 20, right? Because this one will be right from here to here will be only 10, right? So you see from here to here is 86. So what will be this distance, like from here to here? Let's how much? This distance will be 100 minus 86. That means this will be 14, right? 14 and plus 10, half of 20. This plus 10, right? From here to here. So 24. 24 D square. That I put it over here. This is the area into 24 D square. Why 24 d square? 1 by 12 b h cube is giving inertia respect to the CG right over here. But we need to figure out respect to this point. So that's why we need to use the parallel axis theorem, that I equal to ICG plus A d square. That you already know in your engineering mechanics class. Okay. So we already finished with the top area. Now we have to take the bottom area. Bottom area. So again, formula 1 by 12 B H cube. In that case, B is 0.2, AC is how much? 100, right? The 0.1 whole cube plus AD square. So A is the 0.1 into 0.02. This area. What is the D? So you see CG of the top portion. The not top, the lower portion, right over. What is the CG? At the midpoint. At the midpoint mean distance from the, if I take something, this right over here. So what is the distance from the top to over here? This much. Obviously 50, right? And distance from bottom line to this CG is 86. So what is the difference between two CG location? 86 minus 50, so 36. So right over here, 36 whole square. That means AD square. D is the 36. So you got the IXX over here. Now you need to figure out the IYY. IYY mean you need to figure out IYY with respect to this vertical axis. So similarly, we need to work with two area, top area and the bottom area. I think I have to figure it again over here. So you see, again you take the two area. First take the top area. 1 by 12 B is cube. So it's 1 by 12 and B is how much for the top area? For the top area, B is 0.2 and 150 is the height, because we are trying to figure out with respect to y-axis. So right over here, we are getting 1 by 12 B is cube plus AD square. This inertia I highlight with the black color. That one you are getting with respect to this point at the, let's see, respect to this point, right? But we need to figure out respect to this point. So what do we need? Plus area into d square, right? But you see, we're trying to figure out along y-axis. So if I say this is y, this is x. So along x-axis, see difference of distance between two CG actually 0. So there is no AD square. So I just keep it 1 by 12 B H cube. Similarly, the bottom part, B will be 100 and H will be 20. And his CG will be at the midpoint of right over here. So again, the distance from the y-axis, this CG and this CG is same. So D is 0. So this is my IYY. This is I'm getting 1 second. So this is my IYY. And this is my IXX. Okay. So then you figure out I minimum equal to this mass. You figure out radius of gyration, I minimum by area. Obviously, it has a unit. It's a radius. Okay. Then you figure out L by K. K value is here. L is 4 meter. You got L by K. Then you need to figure out critical slenderness ratio. L by K critical. So what is the formula? L by K critical equal to this one. But I put L by K equal to S critical SR, then figure out the value of SR instead. Okay. So we getting 0.8. So you see your L by K, this mass, and slenderness ratio, critical slenderness ratio is 8. So you are in the right side or left side? The column will be long or short column. If you look in this graph, okay? So in this graph, you see this is critical self-damage ratio, right? This point. So this value right over here is 8 point something, but our L by rho value is coming 118. That means we are in the right side. That means we need to use Euler equation of column. So write down over here L by K greater than L by K critical. So it is a long column, we need to use Euler equation. So use just this equation. Then this is the stress multiplied by area, you get the critical load. And critical load, 1 second, is pi square. So this mass is the critical load. Okay. Now part B is saying column length 1 meter. So you figure out L by K, you are getting L by K 29, and L by K critical still remains the same. Not the same, a little bit different, because what is our value of C? At the top, both value of C equal to 1, because both end was hinge. So we put C equal to 1. But in part B, it's saying 1 n free, 1 n fixed. So that one is C equal to 1 by 4. So if you figure out self-damage ratio, you got 0.4. Critical self-damage ratio. That means right over here 0.4, and your ratio is 29. But still you are in the right side. That means you need to use Euler equation. So you put all the number in the Euler equation. Right now you got 22,000, about 3,000 kilonewton. And but column is 1 meter short. But right over here you got 700 kilonewton. Okay. Even column is shorter, it carry little bit higher load, right? 2000, because column is shorter, it carry more load, but due to the changing of end condition, its load bearing capacity is going down little bit. If this is the same condition, then this value will be more than that, might be about 4,000 kilonewton. Okay. So this is very simple problem. We are trying to show you that what is the effect of changing end condition and also changing length of the column. Now, any question, anyone? Hello? No question?
No, sir.
No? Okay. Mahfuz, roll 99. You there? Hello? Mahfuz, roll 99. That means you are not there. You are not in the front of the computer. Section A, roll 99. Okay, roll 73. Hridoy. Roll 73. You are not there even. Okay. So we finish this problem. Still, if you have question, you can ask me. Now we'll start something else. Okay. Let's see. Okay, I see this is problem 3. And you see it look like a Z, letter Z over here, right? And there's a lot of dimension over here. This is a material, a kind of bar. Okay, this is the cross section. You see, if I make line, then its 3D body would be like that. Okay, if I get like that, I can connect with this one go like that. Okay, and lot of this type of structure in the airplane, also in the ship, and sometimes you might see in the lot of machineries they're using this kind of extrusion or parts. Okay, so this is a column, and you see geometry cross section a little bit complex. So in that case, normally I give you the area. I give you the IXX, I give you the IYY. So it makes a little bit easier. You can easily figure out I minimum, then you can figure out the radius of gyration. Then you can solve it, right? So this bar is a Z-shaped, made of this aluminum 70766 aluminum extrusion, allowable buckling stress, and load of the bar pin to pin support. That you need to figure out. Find the allowable buckling stress. That is sigma critical and load. Sigma critical multiplied by area, you will get the load. And say pin to pin support. That means C equal to 1. You need to figure out for length equal to 26 inches and also length equal to 16. So one time you might see it is fall on 26 inches, then it may fall down in the Johnson equation, left side. When it's 16, then you see it is going to long column. Then you need to use Euler equation. And value over here, FCY 70 KSI. FCY mean SY or sigma Y, and value of EC is given. Okay, so it's very easy. So I think you're able to solve it, okay, by yourself. Now we look at something else. Right over here. Right over here. Okay. What will be happen? That so far we solved two equations, Euler equation and Johnson equation. And both cases say this is your column. If cross section is a rectangular like that, then your load is going through the center of this body. Okay. Then you can apply Euler equation or Johnson equation. But if load is not going through the CG of the body, say CG of the body, right? In that case, will be say at the midpoint, right? Longitudinal centroidal axis from here to, you see, right over here. Now, if load is working right at this point, say bottom has a support, so reaction will be upward, right? Say reaction at the same point working through over here. So what you see, the direction of load is not going through the centroidal axis, so it will create extra moment. So this distance, that means distance from, I will say distance from here and distance from here, this distance is called eccentricity. So you need to figure out what is the eccentricity and what is the effect. For example, you use pencil box, right? And that pencil box, if you hold it, 1 second, I'm sharing the screen. Let's say I can explain it. Like this is a pencil box right over here, you see, right? So I'm putting bottom on my hand. At the top, I am applying load at the center. Let's see, at the center, I'm applying load. So load is going through the CG of the longitudinal axis. But if I apply load at the corner, then what will happen? And the vertically applying load. You apply too much load, you see, it is tilting. But why it is tilting? Because it creates some extra moment. So this eccentricity, if you have the eccentricity in a column, then you need to figure out that what is the extra load coming due to the eccentricity. So that is this chapter. So you see in right over here in the left side, there is a center line of the column is showing with letter CL. And we apply load right over here. This is the E, this will be E. Now this one, what happened? There is some extra material, right? This one we can simplify the view. We are saying this is the centroidal axis of the member, right from here to here. Second, from here to here. This is the central axis, but we apply load over here. So we're saying instead of structure like straight, it is kind of C. Okay, just for a simplified view. So in this simplified view, now what I'll do, you see this P, load P, is called external load because you can see by your eye. For example, if I say you're walking through the road with a 5 kg bag on your hand, I know that your weight on your head is 5 kg. But how much the reaction of your feet, of your bone, that will be internal load. So internal load, we need to figure out that why column is bent, because at different section, there are some internal bending work. Okay, that's why it is bending moment work. That's why it is bending. But in that case, you will see beside bending moment, there is some extra thing is working. So that also we need to figure out. So what I did, say this is A. I will identify letter A. This is B. Say this is point C. I like to figure out, cut this column at point B. So if I cut it at point B, then the straight line. So this will be line point A, right? That we draw as the point A. Let me take mouse pad, and this one is point B. So what is the load at point A? At point A, we have this load P, upward direction. So load working right over here, upward direction. Okay. So what is the load at point B? How we can figure out? You just make it balance at point B because we are working with the static body. Body is not moving. So at point B, there should be a force working downward. This is upward, it will be downward, right? And obviously this is reaction force. I am putting this side. So line AB, is it balanced now?
Yes, sir.
It is balanced.
No, sir, there will be a rotation.
Rotation, good. What is your ID?
37.
37. Your name?
Sir, Maliha Hamda.
Malia Hamza. 36. Okay, good. Thank you. Roll 57. You are here? Is not here. Roll 58. Sadi. 85. Roll 85.
Yes, sir. Yes, sir.
Okay, everybody is balanced? Yes or no? Did you see everybody in the screen?
Yes, sir.
Tell me, is it balanced or not? This everybody I make with the circle. Tell me. This everybody is balanced or not?
No, sir.
No. What is the problem?
No, sir.
What is the problem? How we can make it balanced then? Okay.
Sir, rotation.
You see, rotating which direction? You see, it is rotating clockwise because this end anti-clockwise, this end pushing upward, and B end pushing down. Same thing. Say you're lying down in a bed, and one of your friend is pushing your head in the north direction, and other friend pushing your leg in south direction. Then what will happen? Automatically you will be rotated, right? This is rotating. So you need to protect this rotation. This rotation actually anti-clockwise. So you need to put a clockwise rotation to stop it, right? That's we did over here. You see, right over here. Now, then how much force will be this point? Just opposite of this force. This is downward, this will be upward. This is anti-clockwise, this is anti-clockwise. Now, if you close these 2 points, this point and this point, then what will happen? You will see this force and this force will be cancelled out. Okay? Because this one upward, this one, I'm sorry, not this one, this force. This force and this force will be cancelled out. Because this is upward, this is downward. similarly, you see the moment, this moment working anti-clockwise, and this is clockwise. So this will be cancelled out. That means if you join together, then this force will be gone. So you see these two forces at two ends, you are not able to see from outside, but you make the free body, then you can see this force. Okay, so what you see that this figure I can simplify it with this load. I'm saying instead of is load is working right this point upward, it has a this point, it has a upward force, and it has a bending moment along this direction. Okay, that we put. Now, so you see in the Euler equation we derive only one force, this vertical force P, compressive force. But in that case, you see there's a two force coming. One is this bending. Now, what will be, how much will be this value of this bending? This bending, this value M will be how much? You take moment over here. You take moment over here, then you will get M equal to P into E. That means you have apply more eccentricity, there will be more bending will work over here. Less eccentricity, less bending. If E is 0, then there will be only M, only P. M will be 0. So you see this point right over here. Now two force working this point. Upward vertical force and this bending. And this bending is, you see, anti-clockwise. This is anti-clockwise. Now, I will cut this beam, this column, say it was like that, right? I cut it right over here. Then try to figure out that how much force is working over here. And all those force will be depend on this value of X. Because the Y value, distance between over here and over here, it depends on value of X. You see X0, no delta, delta 0, delta means Y. And right over here, if X is L by 2 at the middle of the column, then Y will be maximum, that is called delta. Again, Y increase again more delta, Y increase the X or X become L, they see Y value will be 0. So now we need to figure out right over here that you cut over here, how many forces working, that we need to figure out. Okay. So how we can do it? Let me draw the free body in the next slide, or I can draw it right over here. What I'm doing, say this is the, 1 second, the figure is not complete, right. Okay. Let me draw carefully. Actually, it is hard to draw a figure with, say, this end. This end is the at the middle. This is the end. Okay, I cut it, say, right over here. This point is right over here. Okay, so you see the how much load working at point, bottom point. Number one thing at the bottom point, force working, upward force, compressive force, P. Other thing working, a bending moment, you see right over here. This bending moment, right over here, bending moment working, M equal to P, right? And working anti-clockwise. So right over here, there is a bending moment working right over here, anti-clockwise. So this is P, and this is moment. And value of this moment equal to P into E, right? So I need to figure out how much force is working over here. You need to balance one by one. And if I think this is the x-axis, what is the distance from here to here? So this distance is y. Now my target, what will be the force over here? And you see this P working upward. So obviously there will be one more P should work downward, right? So is this balance? Anyone?
No, sir.
Is not balanced, right? Because you see, if you forget about the P into E, still there will be moment, because this and I draw like that, say draw like that, not completely out, everything is gone. Okay, what I'm saying, we draw like that, right? So in that case, right over here, P working upward, right over here, P working downward, still not balanced, because this force working along this line, this is working along this line. That when he is pushing up, he is pushing down. That means rotating. So this is not balanced. So that's why you see, right, if you look this free body right over here, if you look carefully, we have this P. Same thing, we put this P toward bottom direction. Okay. Now we put a moment over here. And this moment, right over here, this moment, and this is the distance between this point and this point is y. And this moment, we don't know which direction. Obviously, it will be anti-clockwise, because clockwise, because what you see, PE try to rotate along anti-clockwise. Again, P into Y, if you hold over here, then he is pushing upward. That means this is rotate along this direction. So both PE and P try to rotate this body clockwise. Again, I put a moment clockwise direction, because for simplification. So if I will get with a negative sign. Now I need to figure out this value of M. So how I can figure out this value of M? You take moment at that point where we cut the beam. Then you say moment, if you say clockwise, CW equal to 0. Then P into E, rotating which direction? Respect to this point, anti-clockwise, right? So minus P into E. Again, this P into Y, this is also anti-clockwise. So minus P into Y, P star Y, star Y, okay? Then this M, already I put it clockwise, so this will be also minus. And you can put positive that other direction, but then you will get the positive. So what I'm getting, M equal to, we are getting minus P into E plus Y. This is M. This M, value of M, where will be maximum? When Y value maximum. Y value maximum will be at L by 2, man, that at delta. So M max will be minus P into E plus delta. This will be your M max. Okay. Now this value of M, we'll use this M, then we'll figure out the stress formula. And that's why it is bending, because always there is a bending moment is what. If there is no eccentricity, then there will be no this term P into Y. Okay, so that means there is a extra bending working there. Now,
Sir,
yes.
sir, sorry to
Sir.
interrupt, sir, but after 3 minutes, we have a quiz to attend, sir. So,
Okay, so we need to stop. Okay.
Yes, sir.
yes, sir.
What is
We
the
can
time now?
continue.
How long we have?
Sir, only 3 minutes left, sir.
Only 3 minutes left. Okay. If anyone hurry, you can left the class, join there. I will finish within 2 minutes, 3 minutes. Okay.
Sir, we have a quiz, sir. Quiz.
Yeah. No, I'll go with the 3 minutes. Let me finish this.
Okay,
this,
sir.
Then you can leave. But if you want to leave, you can leave it now. And if you look carefully through this point, at this point, how many forces there? You look over here. How many forces there? One is axial compressive force. That means P. Other one is bending moment. Due to the bending moment, what kind of stress will be there? Anyone? Due to the bending moment? Due to the bending moment, you study the beam, so your stress will be MC over I. And where this beam bend, then is bend like that, right? So this side will be compression, this side will be tension due to the bending. Again, it has a direct compression. And what is the value of this stress? Sigma equal to P by A. So you see this column experiencing two forces, P by A direct compression, also sigma equal to MC over I. So total force will be P by A plus MC over I. So in next class, we'll derive this equation. Okay. So which lab you have quiz? Hello.
So we have a quiz on theoretical class.
Quiz on theoretical class. Okay. Okay, you can leave. So let me close the screen. Do anyone has any question? No question? Any question? No, right? Okay, so we can stop it here. Alaikum salam. See you on.
I have an issue, sir.
Okay, go ahead.
Sir, I am not added in your classroom, new classroom.
So you add it. You are not able to
Sir,
add?
if you can provide me the classroom code